No, there will be no class on Wednesday because of Founder's Day. Our next class is Friday. But I gotta finish chapter 7. And then if I look at the schedule, no class Wednesday, class Friday for the start of chapter 8. Monday, the homework for chapter 7 is due, and that means we've done chapters 5, 6, and 7. And that's an exam. That exam is Wednesday. So review sheet's already up, you have access to it, but that's where we're gonna go. And that's a week from Wednesday, but this Wednesday we don't have any class. You should all go to the Founder's Day stuff. If I'm working in any normally distributed population, I can compute probabilities by converting to the standard and using my normal distribution for that. With software, I can compute off of any normal distribution. And we'll do it both ways, depending on what we have access to at the time. But let's think about how this operates. I'm going to pull a situation out of the textbook. Problem number 29, page 249, says we're going to choose the bottle of liquid soap. And we are told that the liquid soap is normally distributed with an average of 600 milliliters and a standard deviation of 5. Now, what's the chance? You pick a bottle at random, and that bottle has less than 592 milliliters in it. Again, there are a number of different ways to compute this. But the way I'm going to think about it is what I really need is a z-score for 592. So what is that z-score? Hang on. Walking through my formula, I take the x value in question, subtract the average, and divide by the standard deviation. For us, that's a negative number. That's okay. Now, I'm thinking in the standard normal picture. So I'm thinking about this z value in my standard normal distribution. And 1.6, negative 1.6, can be over here somewhere. Because if this is the standard normal distribution, its center is 0, and its standard deviation is 1. And we want this chance, but that's the same as this chance. So instead of looking at an arbitrary normal distribution, I can jump to the standard normal, and now I say to myself, how do I get that number? Go back and I'll look at this picture. If I wanted you to shade in the region that we're trying to find, where would you shade?
It would be to the left of the negative 1.6.
And now, oh, that's the kind of picture that's at the top of table C2. That's this kind of picture. That's a cumulative distribution function because it's starting all the way on the left and accumulating to some value. So I just need to find negative 1.60. and there's my chance. 0.0548 is this value. So there is a 5.48% chance that the bottle I pick up has a volume less than or equal to 592 milliliters. If I want to use the normal distribution that's in my calculator, second, under the above the variables buttons, it says distributions. There are my normal distributions. And now I can use the CDF that's here. Now you'll notice it's by default set to a standard deviation of 1 and a mean of 0. It's by default set to the standard normal. If you've used something else in here previously, that's fine, you can do that. I'm going to go from minus infinity up to negative 1.6 and ask it to do this distribution. 0.548, rounding to the same number of decimal places, right? If I didn't want to change to z, I could use this same command, distribution, normal CDF, and say I want to go from negative infinity up to 592 when my average is 600 and my standard deviation is 5. And then it does the conversion for me. If I'm in Excel, norm.s.distribution gets me the standard distribution. Norm.dist gets me any distribution, but then I have to feed it the mean and the standard deviation in the command. Question? Now the calculation on the same distribution. What's the chance I pick up a bottle of soap and it is between 592 mils and 603 mils? I believe in the pictures. They tell me what I need to calculate so that I know where to go to get the information I want. What are the z values that I would need to do this in the standard normal distribution? Yeah.
You have to try to find the z value for the 592 and also the 603.
Ah, but I have the z value for 592. It's up there.
So it would be the 603 only.
Bingo.
Then you would go off the chart and.
Oh, but let's just do the z part first. So now I know that in the standard normal, this is the same as saying z needs to be between negative 1.6 and 0.6. I'm going to draw that same picture, but now I'm going to put both lines on it. (0.6) is going to be closer to the center than negative 1.6 is on the left. So now again, I need to shade. I want all of the region in between. There are lots of different ways to figure out this area. If I want to use table C2 again, I'd need to find 0.6 And then that would give me everything from here to the left, but I don't want this part. So I'd have to subtract off this little tail here. But this is the number we already calculated, isn't it? That's that 0.0548 that we got in the previous part. So what I really need is to go find 0.6. Same table. This first page of that table is all the negative values. 0.6 is going to be on the second page. 0.60 is 0.75257. What do you get? Now that's not the only way to get this number. If I look at table C1, notice that table C1 always works from the middle out. And since this picture is symmetric, this table only uses positive numbers. So another way I could do this would be to split this and look at this side separate from this side. And I could think of the side on the right and the side on the left. And I'd add those two together. But the side on the left is the symmetric version if I do positive 1.6. And now those two numbers can come off of table C1. Wrong number. Copy down the wrong number. Got to make sure you copy down the right numbers from the table. And lo and behold, 6709. I get the same result. This is why I like drawing this picture, because it tells me what I'm looking for, and then I have lots of different options as to how to acquire it. Again, depending on what you're using. Questions? A lot of times I want to know benchmarks, the top 10%. We talked about the top 1% in height last time. But here's another example of this. Page 251, problem number 43. Weights of newborn babies in Foxborough Hospital are normally distributed with a mean of 6.9 pounds and a standard deviation of 1.2 pounds. Now, if you know anybody who has been pregnant, you'll notice there's a lot of deal made of the weight of a child at birth. This is our assumed distribution. What is the chance that a baby will weigh more than 8 pounds? This is the exact same type of calculation we just did, right? So I can say, oh, what I really need is the z-score for 8 pounds. Now, if I'm working in my chart, I only get 2 decimal places for z. If I'm working on my calculator Excel, I can be as precise as I want. So this is equal to the probability that z is bigger than 0.9167. Now, first of all, I can already say this is not an unusual situation to have a child whose weight is 8 pounds because the z-score is less than 1. And unusual doesn't begin until the z-score is 2, right? Outliers don't begin until the z-score is 3. So, how likely or unlikely is this? Draw me a picture. Even a crappy picture is going to help. .9167. If I'm dealing with my chart, I need to use 0.92.
You can find on the table what's 0.967 and then 1 minus the.
Aha. I want this piece over here. All of my tables either work from the middle to the right or from all the way on the left to the right. I won't be able to use either table directly to get this. I'll need to subtract. If I think about the whole area is 1, then I could say this is the same as 1 minus the chance z is less than or equal to 0.9167, and that I can get off my chart. That comes right off of table C2. Only in our case, we'd use 0.92 if we're using the table. 0.9012, I get 8212. And that's 0.1788, 18%. Not terribly unlikely. Not all that uncommon. However, that's an average, right? And it is really outliers and unusual items that we are concerned about. It turns out that children born of substantially low birth weight have lots of medical difficulties. My girlfriend worked as an ultrasound tech in Baton Rouge at the Baton Rouge Memorial Hospital, and neonatal ICU had a lot of issues with underweight children. So what happened? How unlikely or likely do I need to worry about these low weight children? And they said for that hospital, the cutoff was 4.5 pounds. A newborn baby who weighed 4.5 pounds. How likely or unlikely is that? Is that really an outlier? Or maybe I should look strictly at outliers. What's the weight that goes with an unusually low birth weight? Well, unusual means a z-score of 2. Low means it's going to be a -2. If my z is -2, what weight is that? I'm going to work backwards, right? I want to find the weight. The weight's the x value. I was given the z value. Let's solve for x. 4.5 pounds is considered an unusually low birth weight. Therefore, special care should be taken with any child whose birth weight is 4.5 pounds or lower. At this distribution. Outliers. If I wanted to find outliers, I'd say, oh, well, we should look at z equals what for an outlier?
-3.
That's for the low end, and +3 for the high end, right? Because things like gestational diabetes can cause high birth weight. There are lots of contributing factors. The hospital decides it wants to know what's the top 2.5%. I want to find a top number. I'm going to look to something on the right. But I don't know the z-score. What's this? If it's not a z. Jacob?
I'm not sure exactly what that'd be, but couldn't you just do, so since the whole normal distribution would equal 1, couldn't you do 1 minus 0.025?
But that 0.025 is there for this little bit, isn't it? This is 0.025, and that means this is 0.975. So if I can find the z where that line is drawn, I've now figured this out. Now I am going to tell you that both of our normal distribution tables use this number a lot. Matter of fact, here in table C1, I'm not going to find 0.975. In this table, what am I going to find instead? Why 0.1? No, I want to keep the regular. Don't want to round anything. But if this is all of the stuff to the left, table C1 only looks at this stuff. How much white area is here? Unshaded area. 475, because I take away a half. The left side is 0.5. Please notice, there's a box. Around the number 0.475, that's how often this shows up. And it goes with the number 1.96. That's our z value. The z value in this question is 1.96. What we've done is we've used our normal distribution backwards. We've inverted our function. If you're on table C2, on the positive side of the chart, you'll see 0.9750, but there's no box. What you will see on the negative side of the chart is negative 1.96 as the box for 0.0250. That's the mirror image of the picture we drew. But in either case, that's a value we're going to use a lot. Well, now I do the same thing we just did and figure out where the cutoff is, what the weight is. But there's a way to do that here as well. On my distributions, I'm using my normal backwards. That's what an inverse does. The inverse normal, what's the area I want? If I wanted to do with the 0.975, 1.96. Same exact answer. But I have to remember that I'm doing from the left all the way up. That's this part for the inverse normal. Norm.inv or norm.inv works in Excel. It depends on your application as to what you really want to know out of the situation you find yourself in. Bottom of page 251. An auto shop notices oil change times have a mean of 28 minutes and a standard deviation of 5 minutes and are roughly normally distributed. But what I've done is I've observed the data and I've been able to say, with our descriptive statistics, I did an analysis, the average is 28 minutes, the standard deviation is 5 for all of the oil changes you guys have done for the last year, employees of my shop. So I'm going to use this idea now to figure out what's going on with my shop. What is the chance that I'm going to take an extremely long time, let's say 45 minutes, to do an oil change? If I know what's the chance of being more than 45 minutes? I can say right away, this should be a very, very small number. Why?
Because 3.4 is an outlier.
All the way out there. So this should be a very small number. Remember, our normal distribution, 99.7% of the stuff is inside 3. So the stuff that's outside 3 is already 0.03, 0.3 to begin with, 0.3%, 0.003. So when I get all the way out to 3.4, I'm way the hell out there. I'm after that little bitty area. Again, this is a tail. It's only outside, right? It's a tail. So if I'm going to use table C1, I'm going to have to subtract. If I'm going to use table C2, I'm going to have to subtract. I'm not going to be able to use the CDF as given, because the CDF either starts from all the way on the left or from the middle, depending on which version I'm using. Which one do you want to use, C1 or C2? We're all so lively. C2? If I'm doing table C2, then this is 1 minus the chance Z is less than or equal, strictly less than 3.4. Remember, the chance of hitting exactly a number doesn't really matter. But now I can go to table C2 and I can look up 3.4. Here's the positive part of table C2. 3.40. 0.99966. As a percentage, that is 0.034%. 3 chances in 10,000. It is very, 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 very unlikely that an oil change at this shop will take 45 minutes or more. However, if I tell you on average it takes 28 minutes, when are you going to start getting pissed off about your car taking too long? That's a legitimate question. If I tell you something's going to take 28 minutes, when do you start thinking, man, this is taking forever? Some people, the answer to that question is 29. Some people, the answer to that question is 20. I don't know. But if, for some reason, you could say, man, I think I've had a number of ones where people have complained that things have run long. Maybe I should offer some sort of discount. Now you can say, well, where do I draw the line? How many discounts do I want to give away? 5%? Top 5%? Anybody that's in the top 5%, they should get a discount? Maybe it's the top 2%. What's the right line to draw? This is a business question. I don't know the answer to it. I don't know business. But if I said that the right line to draw was the top 5%, I could ask the question again. What time represents the top 5% of oil changes? What am I looking to find?
It's not like the previous one, you can see the 95%. Then we see in the chart, and we can find that.
So either I need to find the cutoff line for 45% if I'm using table C1, or 95% if I'm using table C2. So grab tables, or what else could I do? If I wanted to use my technology. Which technology do you want to use? Come on, people, talk to me. If I'm using my technology, what am I going to try and find on that technology? Jacob?
I found the. Well, you have the areas, you have to find the Z-score.
And that means I'm taking the normal backwards. That's my inverse. Whether I'm using the calculator to do the inverse normal or Excel to do norm dot inverse, I can do that backwards. This is an inverse problem. And yes, when I do this, if I do this on the calculator, I'll get a Z-score of 1.645. If I look on the charts, I will see the number that I'm looking for, 0.45, right, is exactly between these two, 1.64 and 1.65. So I split the difference in half and do 1.645. And now I can convert that back to a time. So if I'm telling you that the top 5% of people, top 5% of times, are going to get some sort of discount, then the cutoff time for that is 36.225 minutes. Which is a lot closer to 28 than I thought. But that normal distribution line, that tail only gets really thin once we're Z'd out past 2 or 3. Questions? Yes.
Next we can use C1 and C2.
Yes, you'll be provided with them. They'll be on the exam.
So we can choose.
Whichever way you like. Just explain to me what you did in your exam space. On page 245, there's a list of numbers we're going to see a lot when we're looking for this inverse normal idea. If I'm looking for 25%, wait a minute, 20, that would be the quartile, right? Q3 would be the 25% mark on that side. Then I'm at 0.675. But if I want 25% in the middle, that'd be 0.5, right? 25% on the left, 25% on the right. It'd be between 0.675 on this side and negative 0.675 on this side. So I'm looking for the between ranges. Notice that those are twice because there's a tail on each side. And lo and behold, 0.05, there's the 1.645 I was using. 2.5% versus the middle 95%. There's that 1960. Top 1%, 2.326. I circled those. I use those the most often. This is on page 245. If you don't have technology in front of you all the time, it's good to at least have these numbers. But they also go with our 1, 2, and 3 for the empirical rule. 68%, 95%, 99% as well. Questions? There have been a lot of formulas in these 3 chapters, 5, 6, and 7. 6 and 7 have all these different distributions, the uniform distribution, the binomial distribution, the continuous version of the uniform distribution, the normal distribution. Back in 5, we had all those probability formulas. There's a lot of shit here. You get a formula sheet. You may write one side of 1 8.5 by 11 sheet of paper with any formula you want to use on it, a definition, formula. You may not include worked out examples. If you look at the review sheet, I believe it says that at the top of the review sheet. We've finished chapter 7 today. That's more than enough for me for an exam. That homework is due a week from today because we don't have class on Wednesday. And that means that Friday, I'll start chapter 8. There are lots of other distributions we can create. As long as I follow two rules, that my function is always bigger than or equal to 0, and the total area under that graph is 1. Any function I create that satisfies those two rules can be used as probability. And that means that I could talk about the Poisson distribution, the exponential distribution, the triangular distribution, forget it. I'm going to spend a whole ton of time with the normal distribution. And the reason for that is based on sampling. One of the things we do to come up with a normal distribution is we gather data. That's how this guy who ran the oil change shop went and got that the average time is 28 and the standard deviation is 5 minutes, is he looked at all the oil changes they've done in the past year. And that was what he came up with. Why can I really only use a normal distribution? Turns out that when you sample, normal distributions fall in your lap. No matter what the underlying distribution really looks like, when you sample, you get something that is normally distributed. That's a piece I hope I will get through on Friday. It's called the central limit theorem. There is a lovely set of videos by Grant Sanderson on channel 3 Blue 1 Brown. I've linked to them in our web links. If you want to look ahead, he's a good, fun guy to watch. I will see you all on Friday. Have a wonderful rest of your day.